So in this video, we're going to look at polyprotic acids. We're going to look at the fact that they don't have a single Ka because there's many protons that can fall off. And we're going to look at how to do a pH calculation. So a polyprotic acid is one where there's more than one proton per molecule. And because there's more than one proton per molecule, then we've got to write out multiple Ka reactions. And I'm going to go with a diprotic acid. So a diprotic acid is one with just two protons. And the same thing is generalized for 3 protons or 4 protons, but I'm just going to go ahead and stick with 2. I'm going to write it as H2A. And the equilibria that I'm going to worry about is H2A, and it's reacting as an acid, so it's going to react with water, and it's going to push a proton onto water and turn it into the hydronium ion. And if you lose a proton, then it's going to be just HA, and because a proton is positive, then you leave behind a negative charge. This equilibrium has an equilibrium constant we call Ka, but because there's more than one proton and each proton is lost one after the other, I'm going to write that as Ka1. That acid, Ha- is capable of losing the second proton, and notice it's not doing it all at the same time, it's doing it in steps, and it's going to form the hydronium ion, and at this point here it's lost all its protons, so it's A, and if it's lost a second positive charge, then now it's got a second negative charge, so A2-, and that equilibrium constant is called Ka2. And in general, Ka1 is much bigger than Ka2, normally by about 3 orders of magnitude, because every time you lose a proton, you create a negative charge, and to pull another proton away from a more and more negatively charged species just gets harder and harder and harder. So, for instance, let me show you a chart of some Kas. So this is from our textbook here. So sulfuric acid is diprotic. In fact, the first proton is lost. It's a strong acid, so it completely comes off. Ka is so large it's hard to measure. Ka2, though, you can see is 10 to the minus 2, which is still pretty significant. Oxalic acid, you can see there 10 to the minus 2 for the first proton, 10 to the minus 5 for the second one. So about 1,000 times harder to lose the second than the first one, and so on. So here's phosphoric acid, the acid in things like Coca-Cola and Pepsi-Cola, and you can see each proton gets harder and harder and harder to remove. And so these equilibrium constants just get smaller and smaller. And we'll do a problem here in a second with carbonic acid. And so we'll see that the first proton has a Ka of 10 to the minus 7, and the second one is 10 to the minus 11. And so that's going to make it a fairly gentle, a fairly weak acid to deal with. So let's calculate the pH of a diprotic acid, carbonic acid. And carbonic acid is a weak acid. Ka1 is 4.3 times 10 to the minus 7. And Ka2 is even smaller. It's 5.6 times 10 to the minus 11. So very, very small. We're going to see that the first proton is barely lost, and the second one is really, really barely lost at all. We're going to approach this as a 2-step problem. So we're actually going to go ahead and we're going to look at the Ka1 reaction first, and then we're going to go ahead and kind of mop things up with the Ka2 reaction. So the Ka reaction is always the acid is reacting with water. And what makes it an acid is that it is capable of donating a proton to water to convert it into the hydronium ion. And then what's left behind, right, is the conjugate base, so HCO3-. So notice even though this is a conjugate base, it has a proton that can be lost, so it can also act as an acid. So we go ahead and we write out the ice chart. So we've got initial, change, and equilibrium. And so we're dealing with 0.1 molar. Okay, initially we're going to say 10 to the minus 7 is hopefully small enough we can ignore. The change, like all of these ice charts, right, whether it's 1 to 1 to 1, is minus x on the side that loses and positive x on the side that gains. So at equilibrium, 0.1 minus x, hoping that that 10 to the minus 7 isn't going to matter, and x. All right, so now we're ready to calculate. So Ka1 is equal to the concentration of products over reactants, and actually, let's go ahead and take the value, 4.3 times 10 to the minus 7. Is equal to x times x squared over 0.1 minus x. And again, we're going to make that approximation because solving the quadratic equation is such a pain that x is much smaller than 0.1, right? So we're making this approximation that x can be neglected in the denominator. And the reason for that is that makes the problem much easier to solve. So x squared is just 0.1 times 4.3 times 10 to the minus 7. That's 4.3 times 10 to the minus 8. And we want to know x, so x is just the square root of that number, and when we square root that, that is something times 10 to the minus 4. Let me see, 2.1 times 10 to the minus 4 is our assumption that x is much smaller than 0.10 K. We have to calculate the 5% rule, and what we find is that that is only 0.2% dissociation, so it is way under that 5% rule. And remember, if we're off by more than 5%, our pH will have a measurable error. All right, so here's the story now. So we're going to go ahead and we're going to look at the second proton coming off of this guy here. I'm going to write the Ka2 reaction. And unlike before, where we can assume that the hydronium ion concentration is pretty much 0, we're going to start off with it being equal to this value of x we've got here. So I'm going to go ahead and push the screen up and just kind of carry on with this problem. All right, so we can start with the Ka2 reaction here. So what do we have now? We've got HCO3 minus. It's capable of losing another proton to water. And so it's going to form the hydronium ion when it protonates water. And at the end of the road, right, it's going to form carbonate. There's no more protons to lose. We set up our initial, our change, and our equilibrium, whereas before, we would assume a lot of these on the right-hand side were 0. Now we've already got these concentrations. So the bicarbonate concentration, that's x in our previous problem. So that's 2.1 times 10 to the minus 4. Again, water is a liquid, so we have an effective concentration of 1. We pretty much ignore it. And the hydronium concentration, right, we would assume it's 10 to the minus 7, or we'd assume it's about 0, but we've already solved for that in step 1. So this is the thing. We're going to go ahead and we're going to take the value from step 1 and use it in step 2. And again, we've got no carbonate yet. So we lose from the side on the left and we gain from the side on the right. So we don't have any carbonate, so we know we must be dissociating and making some. And at equilibrium, we can just sum those two together. So 2.1 times 10 to the minus 4 moles per liter minus x, and then 2.1 times 10 to the minus 4 moles per liter plus x, and then plus x. And what do we got here? This is the Ka2, and we're told in the problem that that was very, very, very small, 5.6 times 10 to the minus 11. And because it's so small, we can probably assume that x is going to be negligible here. So our products are 2.1 times 10 to the minus 4 plus x in concentration of the hydronium ion. The carbonate concentration is just x, and we're dividing it by the concentration of bicarbonate, and we've solved for that. So that's 2.1 times 10 to the minus 4 minus x. And if we assume that x is much, much smaller than 2.1 times 10 to the minus 4, that allows us to say that is approximately equal to 2.1 times 10 to the minus 4. So adding x to that won't change it, times by x, all divided by, on the bottom, we got 2.1 times 10 to the minus 4, and we're subtracting x is not going to change it. And the beauty of this is that notice that this is the same number on the top and the bottom, so it essentially cancels out. And so Ka2 is pretty much equal to x. And remember, Ka2 then is equal to x, so the concentration of carbonate is essentially equal to Ka2. So it's equal to 5.6 times 10 to the minus 11 moles per liter. Now, in terms of calculating the pH, right, technically we're supposed to be adding 10 to the minus 11 to 10 to the minus 4, but we can see that 10 to the minus 11 is what, 10 million times smaller, so we can pretty much just neglect that there. We can see that that's not even 5%. So the pH is just going to be based upon this concentration here. So let me just push the screen up and finish off this problem. All right, so at the end of the day, then we can calculate the pH, and that is equal to the negative log of the H plus concentration. And we've already solved for that. That was 2.1 times 10 to the minus 4. And that has two significant figures, so that gives the pH to 2 decimal places. And I get 3.68. And since it's an acid and it's at room temperature, it should be less than 7. So that makes a lot of sense. And again, just to recap, so we've got these two different equilibria, and we kind of use the one and let the first one feed into the second one. But we can see pretty much all the hydronium ions are coming from that first equilibrium, that Ka1. There's very little coming from the Ka2 reaction. And for weak acids, that's generally almost always the case.